Hi everyone, welcome to VSAONLINE, and today it's my special pleasure to welcome Staffan Larsson from Gothenburg University in Sweden. I'm very excited to host this talk about bridging between time-based and computational neuroscience approaches. So, Staffan, without any further delay, please, the floor is yours.
Thank you very much, and thank you for inviting me. And very happy to present this to this audience, which is a bit different from the audiences we usually present to, which is more linguists, computation linguists. And this is joint work with Robin Cooper, Jonathan Ginsberg, and Ander Lücking. And I believe that Robin is here as well. So this was presented at a conference this summer, and yeah, I think I'll launch into it. If you have any questions about like comprehension, things that I should explain more, just let me know and I will try. And then we can take longer discussions at the end. So, okay, I will start with an introduction, then some background, previous work in this area on questions and answers, and then dealing with questions using lambda calculus, proof of concept model implementation, and then conclusions. So the reason we're interested in this is that understanding how semantic representations are instantiated in biological neural networks, brains, remains a fundamental challenge in cognitive science and in semantics. The semantic pointer architecture, as I'm pretty sure you all are well acquainted with, has been used to build what is currently the world's largest functional brain model, SPAWN, by Chris Smith. SPA includes perception, decision-making, and motor control systems integrated in a cognitive model and implemented using spiking neurons, capturing detailed characteristics of the brain. Oops, that was suddenly... Wait. The presentation jumped. I will just go back. So I get a quick backwards look at the slides. So one nice thing for us as computational semanticists is that it allows retaining compositional analysis of natural language in a transparent and biologically plausible way, which contrasts, for example, with large language models, while retaining the robustness of vector processing. So this paper will begin to address this challenge by focusing on the processing of questions and answers, which is one of the fundamental semantic challenges. And we will use a VSA approximation of lambda calculus and show how it can be implemented in neural networks. So for the background, I'm not going to try to lecture to this audience about these VSAs and holographic reduced representations and so on. You are much more acquainted with this stuff than I am. But, you know, they used circular convolution for binding, which is hugely useful. And you have these operators, the bundling and the unbundling, and the binding and the unbinding using the inverse. And in particular, I mean, I won't go into these details anymore in this talk, only to use the relevant properties of this, of the HRR presentations, such as A bundled with B being similar to A bundled with B but unbundled with B is also similar to A, maybe even more so. A bound to B and then you unbind A using the inverse is similar to B, and C with unbound A is similar to B if and only if C with unbound B is similar to A, and there's the identity vector. And of course you also know that the vector manipulations are lossy. For example, the inverse is not an exact inverse but just an approximation, so for this reason you end up needing cleanup memories, and we will be using that a lot. And then the neural engineering framework, of course, implements the vectorial presentations and manipulations in neural simulations, and even more specifically, the semantic pointers that are structured representations in high-dimensional vector space. Dereferencing, yeah, I mean, you guys all know this stuff. So even in Chris's book, How to Build a Brain, he has examples with the questions and answers modeled as semantic pointers, and that's the sort of starting point of this paper. Yeah, so to clean up high-dimensional vectors, we used dot product and similarity vectors. I'm not going into details about that. I'm just going to use a cleaning operator with a optional indication of the domain of the cleanup function. Okay, so now comes the more new stuff to this audience, which is TTR, which is a type theory with records. Robin has a book from a few years back which details this. So it's a type theory where a central thing is, of course, a judgment that something is of a type. Some entity of some kind is of a certain type. Types may be either basic or complex. So some basic types in TTR is int, the type of individuals, or there's the type of integers and the type of real numbers. Those are basic types that they don't have any structure. Then there are complex types, which are structured objects that consists of other objects. One such type is the p-type. So that's constructed from a predicate and arguments. And here's where we begin to approach natural language semantics. So, for example, a p-type man A, that would correspond to maybe a natural language sentence that A is a man, or a specific person is a man. Or CAB, where A and B are individuals, would mean that A is seeing B. Or sees B, rather. Lambda or WH questions, that's, questions like who, what, when, and so on. You can represent those as lambda abstracts over types. So that means you take something like the dog chases the cat, chase, dog, cat, and the indices here are just to indicate that we're talking about a specific dog and a specific cat. From that, you can abstract over the dog, for example. Then you get lambda x chase x cat, which corresponds to something like who chases the cat. Or you could abstract over the cat, and then you get lambda x chase dog x, corresponding to something like who does the dog chase. You could also abstract over both of these. Then you would have lambda xy chase xy, which is basically who chases who. So that's not going into detail about TTR now. There's plenty of detail of TTR in other publications, and specifically on questions in TTR by both Robin and Jonathan, who's also here now, I see. Great. So they can stop me and say if I say something wrong, or if you want to add anything. So the complex TTR objects are constructed from labeled sets. So this is one reason that we think this will work quite well, the connection to SPA, because these labeled sets correspond to structured objects that Eli Smith in his book achieves using superposition and circular convolution, bundling and binding. So we had a paper a couple of years ago where we started this. So for example, if you take something like the dog chases the cat in TTR, that p-type is really just sort of it's actually this set of pairs. So predicate chase, the argument 1 dog 52, argument 2 cat 43, and this corresponds then fairly straightforwardly to a bundle of bindings in SPA. So you have predicate bound to chase, argument 1 bound to dog 52, argument 2 bound to cat 43. Okay, so that was the only thing about TTR, but we'll be able to do some stuff with this. So if you look at what's been done on question answering using these representations in SPA, then you could say you have something like this. The dog chases the cat again. You have sort of a flat role filler structure like agent dog, frame, chase, theme, cat. You can see that this is similar to the representation we were looking at before, but it's just the different labels like agent, frame, and theme. We had argument 1, predicate, and argument 2 instead. But on this take on things, then the WH questions are associated with a certain role here. For example, if you had asked like, who does the dog chase? That you would find the answer to that by unbinding this S here with theme, the inverse of theme. So that would give you cat 43, which is the answer to the question. So that, of course, in this account, you assume that the answer has been found. So you have this structure here, S, with the answer to your question. But also, it doesn't cover everything you want to do in semantics with questions and answers. It does show you how to extract an answer from a sort of role filler structure, but not how to, for example, combine a question and an answer into a p-type. So if you had a question like, who does the dog chase, and the answer the cat, how do you put those together into the the dog chases the cat? And Elias he doesn't also think that this is a complete account. He says it doesn't have a solid linguistic justification. At the same time, on the semantic side, things are not perfect either. So accounts of question answering in formal semantics typically completely ignores the neural dynamics and memory aspects of it. So that's the reason to try to bridge this gap between the neurocomputational and the formal semantics. So let's get to the core of this, how to deal with questions using lambda calculus in SPA TTR. So SPA TTR is this hybrid thing that we're developing, basically mapping from TTR onto SPA. So an account of questions and answer processing, you need to address a couple of questions from a sort of linguistic viewpoint. First, how are questions and answers combined to propositional types or p-types, predicate types? And how can answers to questions be found in memory? And along the way, we also cover type checking of answer candidates and also things like who chases who. We have double abstraction. Actually, that's only in the paper. It's not in this presentation, the double abstraction. But it can also be done. So we're going to use this role filler approach, but a variant of it. So let's first look at combining a question and an answer into a p-type. So this is relevant, like if you imagine you want to model that somebody asked a question, who does the dog chase, and somebody answered cat. What have you learned from this? Somehow you need to put together the question and the answer to a proposition. The dog 52 chases the cat 43. So if you do this in lambda calculus, you would do this by having a question. So here we have lambda abstraction with the added type checking. So you have lambda v of type int. So if you have something of type int, that is an individual, then this will give you the p-type that the dog chases that individual. So if you have an answer, cat 43, you can get the proposition by just applying the question function to the answer. So that will just put cat 43 wherever there is a v in this p-type. So you get chase dog cat again. So now how can we do this in SPA TTR? So we have to convert the lambda abstract, the question, into a labeled set. And in TTR, the questions are also labeled sets, but they have sort of embedded structure. So you have a lambda int, and then you have a pair consisting of body, and then another set of ordered pairs, where you have the equivalent of the p-type. But here, instead of the argument, you have a sort of a placeholder for that. So we do something inspired by this. We do something slightly different. So first of all, we let the abstracted field, this arg2 here, because it's like who does the dog chase, so we have abstracted over the cat here. So then we have the identity vector in the value there. We add a field lambda path, which is the path in the question body leading to the abstracted field. So body, and then you put in this arg2 here that will give you the thing you have abstracted over. And then lambda type in, that's the type of the thing you have abstracted over. And this is sometimes called De Bruyne indexing, which is a way of coding lambda terms without using variables, but instead using paths to mark positions. So now we see that we don't have just like a flat kind of structure, we actually have a recursively embedded kind of structure to handle questions. Okay, so we have that question, and now we have an answer like cat 43, and what we want to get out of this is the dog chases the cat again, so this is the p-type that we want out of this. So in spot TTR Q and A, this Q here and this A here are inputs to a network that does lambda function application, that so combines the question and the answer into a proposition or a p-type. And it does that by realizing the SPA function here. So F that takes a question and an answer. So what it does is it unbinds the body of the question. So this bit here. It subtracts the path, which is the value of Q lambda path, arg2 in this case, and then adds arg2 bound to the answer. So if we look at the example, we will get P if we provide Q and A to this function. So we have Q with unbinding the body minus arg2, or unbundling arg2 and then bundling it with arg2 bound to A. So that will replace the lambda abstracted variable with the argument that you had there. So path equals Q lambda path prime, so that's the inverse. We'll evaluate with some noise to arg2, so then we get P equals, so we had this Q body with body unbound, so we get this. And we unbundle arg2, so that will give us these two fields, and then we add this, so we get that. In a way, pretty straightforward. Still, took us a while to figure it out, and we also got some help from Chris Eliasmith. But it actually works, so that's nice. Of course, to reduce noise, we can add a cleaning operation over the domain of possible paths here. So to figure out this path argument, for example, we know it has to be one of the possible paths of in P, arg1, arg2, or pred, so we could clean up over that, for example. So then, okay, basically this covers for WH questions how you can combine questions and answers into p-types. And this actually works, the same account works for double binding, where you have who chases who, and you apply it to a dog and cat, you will get the same. So that's quite nice. Are there any questions so far about this? Anything I should, I'm used to talking to semanticists who are well acquainted with the opposite part of the one you're acquainted with, so maybe skipping over things.
Tony, please go on.
Yeah, I had a question. So where on slide 32, so where does the answer come from? Or are you just assuming that that's available and you're showing how to construct the p-type that you want?
Which one?
So cat 43 that you...
Yeah. So that's the input to this function. We're giving it a question and an answer. So imagine you're in a conversation and you ask who does the dog chase? And the other person says the cat. And now in your brain you have to put these together, your question that you just asked and the answer they gave. so that you
Yeah.
understand it. Yeah.
Yeah. Okay. Okay.
So
Thanks.
that's where it comes from.
Connor?
Is it can you hear me, or is it, I'm having problems? Is it hear me?
It's a little bit of distortion on your sound.
Yeah, I
The
mean,
Bluetooth, yeah. Is this better? I can take it out. I'm so sorry.
you probably can use chat function because I mean there is huge distortion.
Yeah. Okay. No worries. No worries.
Please continue, Staffan.
Yeah, okay. Right. Okay. So one thing, a little detail I skipped over here is the type checking, and since we have a little bit of time, I think I'll try to cover that as well. So in TTR, question is a function that can be applied to an answer to arrive at a p-type, as we saw before. But here you have this step of lambda v colon in, so that means that we should check first that the thing you're applying this for, this cat, is actually an individual, not something else. And this, I mean, if you're thinking, it's not all questions that have individuals as arguments. You could also have things like, what do you believe? You know, they're the thing that you're abstracting over is a p-type actually. So you believe in that the dog chases the cat or whatever. So it can be different things. But so far we ignored this type checking step. And there's actually a neat way of doing this here as well. So I thought I would show that a little quickly. So what you can do is to prefix this function that we defined before with the term that just if the type checking is successful, it will give you the identity vector. And otherwise it will give you noise. So if it fails, you get noise, but if it succeeds, it will work as before. And to achieve this, we just use the fact that the result of binding a vector to its approximate inverse is, oops, sorry, I'm getting lost through Windows, yeah, is similar to the identity vector. So, and then we can compare the type of the answer to this type specified by Q lambda type. So recall that we had this structure here, that the question, which said, here's the type of the thing, right, that you want to apply this function to. So now we can compare the type of the argument. So now we have to do a little bit of extra thing here, because how do we declare that the type of the cat45 is int? Well, we just have here, we assume something simple. We just have a vector, like a bundle of a bundle of bindings that binds every individual to its type, which we call ft here. So it has cat43 bound to int. So if you do ft and unbind cat45, you get int.
Staffan, we have a question here.
Yes.
Ross, please.
Yeah, sorry. So this question is coming from complete ignorance of
No.
type theory and so on.
Yeah.
So I guess my question here is specifically in the context of vector symbolic architectures. What does having types get you? So, and the position I'm coming from here is that so you've got some vector cat43 or whatever. So I would imagine that that's being treated essentially as though it's a randomly selected vector, so that the vector corresponding to cat43, is it always only of type int? In which case that's sort of implicit in the fact that it's just a randomly chosen vector anyway. So I would imagine that out of that context, you're hoping to get extra information from the types to help you constrain the answers you can get. But in this case,
it's not very constraining.
But in this case, if cat45 is always of type int, just knowing that it's cat45 already automatically gives you int.
Well, I mean, so one thing, first of all, things can be of several types in this theory. So that's
okay, good. Yeah.
But also questions don't always concern individuals. They can concern, for example, p types. So you can have something like I mentioned, what do you believe in, or what do you believe?
Yep.
And then you can have like, I believe that a cat chases a dog, and then actually the thing that you answer has to be a p type, and it cannot be just an individual. If you take at least that interpretation of believe, which is has a propositional attitude. Or like, what are you doing tomorrow? And then you need some kind of action as an answer, right? So it's not maybe just an individual.
Okay.
Yeah.
Thank you.
Yeah. No, but absolutely good to ask these questions, because as I said, I'm probably skipping over things that semanticists find obvious, but not to say that the questions you're asking now are obvious at all, actually. In some other type theories, things can only be of one type. So it's so anyway, we use this, so we can look up the type of this answer, and we can unbind it from FT. That will give us the type of the answer, and then we can unbind the type required by the question, and then we unbind that type. Oh no! Then we bind the type of the individual to the inverse of the type required by the question, which will be the identity vector if they are the same, otherwise noise. So then when we have that, we can just put that in front of this function. So now we have this type checking enhanced function, otherwise the same as before. Yeah, so here's the example. Here's the structure we had. We have an answer. The type is ind. We can get that by unbinding. And then this will be ind. Q lambda type will be ind. Q with lambda type unbound. And then multiplying those will give you identity. Of course, here you might want to clean up things, because we're using operations that introduce noise. If you are fortunate enough to have a basic type, then it's not a problem. You just can clean up over all the basic types when you're doing this type checking step. Might get a bit more complicated in other cases, but we're not concerned with those here. That's for future work. So basically,
may I ask you one technical, or actually maybe a bit high-level question? I mean, you are working with real valued vectors here, right? Aren't you?
Yes.
And just to increase my understanding, so when talking about inverse of a vector, so you literally just so it's negative components. So you.
Now you're approaching the edge of my knowledge of the details of this. So, I mean, it's an approximation, absolutely, and the exact how the approximation works and exactly what it is you probably know that a lot better than I do. But we're using. Let's see if that definition was here. Inverse. Here's the inverse definition that we use.
Ah. Okay, so it's yeah. Okay.
So it's definitely an approximation. I'm not going to try to go into this definition
Yeah.
in this, especially in this company. But it gives you, as I understand it, an approximation with some noise. So does that answer your question?
Yes, thank you.
Okay, good. Thank you. All right. Let's see. We were... Yeah, type checking. We've done that. Good. Okay, but I'm not going to introduce the type checking term in the following, just because it adds a lot of notation, but it can be done, at least for basic types. So, okay, so now we know how to put together a question and an answer, given that we have them. But what if you don't have the answer yet? You just... oh, wait, okay, that's the next step. First, we're going to look at how to extract the answer from question and the p-type. That was actually what was done in the by Chris Eliasmith in the book. So we can just show that we can still do that. So if we have a p-type that we know contains the answer to a question, then we can sort of pick out the precise answer from that. So if we have the dog chase the cat as this structure, and so this is the Eliasmith account, then you have the question, who did the dog chase, represented in this way as just a theme unbinding this thing. That worked, but now we want to do the same with our type of question representation that looks a bit different, and we already saw it. It looks like this. Can we still do the same thing? Well, yes, it turns out we can. So if we have that, right, if we have the lambda path here, that will show you what to look for in the p-type. So basically we can now define another function, fqp, that takes a question and the p-type, and takes the p-type, and then it unbinds from the p-type whatever is in the lambda path here, and you get that by unbinding lambda path from q. So for this example, q like above, like here, and p like this one as before. Then a fqp of q and p, you take p, you unbind with q lambda path, and this will evaluate to arg2. So you unbind p with arg2, you get the cat 45, so, or 43, or whatever the index was. So that still works. Good, we know that. And now finally, all of the above assumed that we had the p-type. But of course, if somebody asks a question, you have to, in many cases at least, if you weren't already thinking of it, you have to retrieve the answer from your memory somehow. And here's like a very simple start of that. Of course, this is much more complicated than we present here, but this is a first stab at the problem. Now, we actually have an advantage here with our more developed or more, fully fledged question representation. If you only had theme prime, that wouldn't help you a lot. Like, who does the dog chase? And then that's realized as unbind theme of something, and you don't know what the something is. It won't help you a lot. So somehow want the other components there as well. And actually our kind of question representation that we have is quite useful for that. Okay, but to do this, we need some model of long-term memory. So we're going to have a super simple model of that, which builds a little bit on earlier work where we introduced something called the judgment history. It's basically all the judgments you made before, or that an individual has made. Here we have even a simpler thing. Just we have M, a memory with integers bound to p-types. So that means we have something, at some point, seen something of type P1. We have also seen something of type P2, etc., etc. So these are all the types we have observed. We can think of it like that. So what's now the procedure for finding an answer A to a question Q? Well, first we take the question body, because that's what's going to be similar to something in memory. So we take the question body, we take out this little, thing that wasn't bound to anything, or that was bound to the identity vector, the abstracted variable. We remove that because that's not going to be so useful to us. And then we find some type in the memory which is similar to this question body. And then we let A be the value of the lambda path in that P, which was similar to Q. Okay, and we know how to do that from before. So say that we have Q and P as above, but in somewhere in memory we have this p-type, that the dog chases the cat. The question, if you abstract away this part that the Q lambda path, that's going to be arg2. So the question body is just going to be this pred chase arg1 dog 52. Okay. So this is done now in a little bit of a roundabout way. There, in order to deal with noise, there is a simple way of doing this that we actually use for the implementation, but bear with me and I'll explain this way of doing it. So we look up the number of the type that is most similar to B, just because then we can clean up over all the natural numbers in a simple way. So we can use B as an approximation of the p-type that we're looking for and use it to unbind the number of the thing that is most similar to it. That will be n. And B at least will be quite similar to P, since we know that if you bundle something B with something A, it's still similar to B. And here there is actually something that, you know, this thing here that is the only difference between these. So this part is the same, so this will be quite similar. So now we can define a lookup function that returns the p-type in M, which is the most similar to some type T, which is going to be the question body minus this abstracted field. So we say search M, search memory for type T. We take the most similar thing, we find the number of the most similar thing, and then we unbind from M that number that will give us that p-type. And yeah, so the only reason for doing it in this two-step way is to be able to clean up over natural numbers. And you probably don't want all the natural numbers, but like limited memory, limited integer, highest integer. So there is such a number here for which the if you unbind the question body minus the thing, the extra thing, you will get that n. So it's 423, and then you can get the p-type by searching the memory for that. So we had the answer. The answer will be this formula that we had before, and q lambda path is arg2, so this will be arg2. So now we can unbind p with arg2, and that will give us cat45. But you can put this all together into a function that takes a question and looks in a memory and returns the answer in memory to that question. So it will search. So first it does this. So it takes away the lambda path from the question body. It searches the memory for the most similar p-type, and then it unbinds the value of q lambda path from that p-type. That will give you the answer. Again, you know, clean up is a good idea. But fortunately, the way we represent the question gives you the type of the possible answers, which is in the lambda type field. So we can actually clean up over that. So that then you end up with this fairly complicated formula, but yeah, that will do the trick. So this is basically a function then for finding an answer to a question in memory. And this will eventually, for the case we were looking at, you will in the end clean up over ind for p with unbound arg2. So, which is, you know, since the cat is one of those individuals, it will hopefully find that. So yeah, this works, but it's super simplified, and of course whether it's similar to anything happening in the brain is a topic for future research. We did implement something here. I don't know if Andy is here. That was mostly Andy who did the implementation. He's not here now, but if you ask something about that I can't answer, then I can forward the question to him later. So we oops. I'm having a little bit of trouble. So yeah. So we implemented this in Nengo. We just gave it the memory consisting of 6 p-types: dog chases cat, dog chases cow, dog sees mouse, etc. And then we ask it 3 questions: who does the cat like, who does the dog chase, and who likes the cow. And if you don't have a cleanup, basically things don't work so well. But here it's asked these 3 questions in sequence. Who does the cat like? Now I have to move things around here to see. Yeah, so you have those colors. They're corresponding to the different answers. So without memory cleanup, you get basically cat most active all the time. So that's not very helpful. If you do memory cleanup, you will get first mouse and then cat and cow in close competition, but with cat the winner, and then I think cat over here. So, but it's a little bit, probably you need more cleanup. Probably, maybe having the slightly more advanced search mechanism would help a little bit. Yeah, so without the memory cleanup, not so good, because yeah, mouse always responded to. And introducing, yes, that's what I said. Mouse, cow or cat, and then dog. That's much better. But yes, more cleanup could help. Right, so to conclude, we have sketched an approach to lambda abstraction to question answering in SPA, which allows us to maintain compositional semantic analysis with a biologically plausible cognitive framework. There are lots of things to do. Does the answer you get actually resolve the question? Well, sometimes you can have a proposition that gives some information relevant to the question but doesn't really resolve it. We only covered WH questions. What about why questions or yes/no questions and other types of questions? How can we scale this up but still keep it not having the noise taking over, but actually making it work? And we also want to have a more plausible account of working memory and long-term memory. And there's work done in dialogical semantic frameworks on that, various kinds, for example, COS by Jonathan Ginsberg. And I can also, as I said to Evgeny just before, we actually have the happy news that we got actually VR funding for a project called Semantic Pointers in Natural Language Semantics, for a 3-year project to do some of these things. So I'm more focusing on compositional perceptual semantics, like how you can basically, understand what you see in the picture and maybe answer questions about what you see in the picture and have the compositional analysis doing that. So yeah, thanks for listening and thanks for asking questions, and I'm happy to answer more questions.
Thank you, Staffan, for the great talk. So we have people from Chris Leisman Group here as well. So and we had quite a representative public today. So let's have some discussion. So please, Ross.
I think Peter and Eileen had their hands up before me.
Okay. Okay. Then we go to Eileen.
I thank you, Ross, but I do think you were just slightly before me. But if you want me to go first, it doesn't matter.
But okay, so Eileen, you go first.
Okay. So, one, thank you. This is slightly different direction, coming at this from a slightly different direction from the work that we've been doing. But I should clarify that point. So we have a similar modeling approach that uses lambda calculus embedded in VSAs. We've been doing some work with Nengo on this, and we're coming at it from a different direction from you. Less semantics, more something else entirely. But of course, Connor's background, who is here in the audience, is in similar approaches to semantics. If I'm not mistaken, he might shout at me. So it's not entirely alien, and find this, and I find using type theory for semantics really, really interesting. But it strikes me that it strikes me that the uh, uh, main sort of explanatory power of applying VSA model using Nengo to some feature of a more abstract cognitive theory, such as the semantic theories in linguistics. It strikes me that the main explanatory power of this is in one's ability to use this to propose some kind of neural anatomy that might affect the cognitive process we believe to be going on there. So I'm wondering, since what your work has done so far has been dealing with more like, can we get the representations just there in an Nengo environment?
Yeah.
Do you have opinions on if there is a plausible or reasonable anatomical model that might be somewhere down the line that might affect this kind of semantic computation in the way that you're describing it?
Yeah, that's a great question. I mean, of course, as you say, at the moment we're just trying to get things going and get something going. But further down the line, of course, if you can set up a model of memory which is biologically plausible, and you can show that has effects on language and on linguistic interaction and on meaning and so on, that maybe even corresponds to what you can observe in people, that would of course be fantastic. Because of course if this is correct, that would be likely to happen. Like the exact anatomy of things would actually play a role in what happens. But we're not on that stage yet. But I hope we can get there.
Yeah. Well, I won't take up anybody else's time, so maybe I'll let Ross speak before circling back, because I do have a follow-up, but I won't bother anyone.
Ross, please.
Actually, my question could be construed as a follow-on to what Eileen was saying. I think if you go back to slide 48, I think it is, please, Staffan. I think that was the slide where you introduced your memory.
I just have to move Windows around so I can see the page.
So as you were associating past
48.
justifications with the natural numbers. Yeah, okay. Yeah, so I'm presuming from your subsequent slides that you're treating the representations of the naturals there as being effectively disjoint with respect to similarity. So 1 is dissimilar to 2 is dissimilar to 3, etc. Is that correct?
Yes, that might well be a naive assumption.
So yes, no. I can see. I mean, essentially, just using them as arbitrary indices to the. So you're probably not actually using the ordering properties for numbers or anything like that to do it. I mean, if they're just so if they're just purely arbitrary indices, they may as well have been, instead of 1, 2, and 3, they could well have been, purple Thursday and not feeling too good.
Absolutely, as long as you have a way of cleaning up over them.
So then, if you're binding what's essentially a random vector, 1, 2, or 3, with the P, then that is the binding is dissimilar to both of the original components, which would then make, if you're then trying to retrieve a value in there on the basis of similarity, might make your retrieval difficult. It depends how you're trying to get the value out. Are you querying it with the inverse of?
So this is querying it with the inverse of the question body, like the thing
right.
We have,
and then getting the natural out. And where I was heading with that is because Eileen was talking about anatomy, and I was sort of heading towards a less constrained version of anatomy. So you're not necessarily. I think the natural interpretation of Eileen's question is, can you get out human anatomy out of this? Whereas I'm heading more towards, could you get out a synthetic anatomy, if you like, which is something that makes sense. So where I was heading was in terms of, can this be implemented purely in terms of natural VSA operations? And so all of us who've done any empirical work in this area tend to do things where we'll wrap some stock standard procedural programming code around VSA operations and say, oh, we're doing this because it's simple. It's not actually theoretically relevant. But you might end up doing things which actually can't be done if you are constraining yourself to use only VSA operations. So with your cleanup here, what people sometimes do is, for example, they'll just basically iterate through a list of everything that's in their cleanup memory, in their dictionary. Calculate similarity, accumulate list of similarities, and then iteratively say, well, I'll choose the highest one with a procedural language, and that's the answer. But that's not the way you do it. If you're constraining yourself to use only VSA. So in this case, probably not, because you say you're querying with the inverse of T. But I think that it's possibly then just something to be wary of when in your future work is, by all means, go ahead and use procedural code to do something as a strategic choice. But I think it's useful to know that if what you're doing is natural or difficult, using only VSA operations.
No, absolutely. We want to do that. So I should really point out that this memory model is just I would say a placeholder for an actual memory model. We don't have one, but we needed one, so we came up with this.
I'm pretty sure I recall from Tony Plate's thesis, where he was putting together a representation of some proposition or other, so using a similar sorts of techniques of a bundle of bindings, and pointing out that if you then bind this with something other else, then the similarities to probes are not visible. So you need to then either embellish that representation with the components as well, so that the similarities are visible or not. But it's been a problem that's been around forever.
Okay, but thank you very much for that. That's definitely something for us to look more into and understand better. And we definitely want to be able to do things with VSA only, and not have to use other code, because we do have ambitions to have this be biologically possible, if not plausible. So thank you.
Thank you.
I saw a raised hand from Connor. So do you want to give another try, Connor?
Yeah, can we let's try this again.
Okay,
I'm going
good.
to try to speak as clearly as I
clearly.
can. Yeah. I'm going to speak as loudly and clearly. I dropped my headphones. I'm so sorry. I work with Eileen. I'm a lab mate with Eileen. And our previous implementation of doing the lambda calculus, we did a very naive solution, and we carried around like an associative memory as the environment. And then whenever we wanted to perform substitution or lambda application over an abstraction, we actually went in and decoded the representation, which is quite similar, I think, to this SPA TTR representation. The question I was wondering was, are you going in by hand and just like intelligently placing your path, your lambda path, like de Bruijn indices? Because I know traditionally de Bruijn indices are like a second step from like a higher level representation. Like you go in and then remove variables and then replace them with like their first bound occurrence in lambda extractions.
Right. Okay. We haven't said anything about that here, so that would be. And please, Robin or Jonathan, if you want to fill in, please do. But I would take that to be part of the natural language interpretation step here, which we're like completely glossing over. It's like, how do you get from what somebody said to this representation of it? We don't necessarily have to go via some other lambda representation, but we definitely need some way of accounting for how you get from a natural language string to this. And the stuff you're talking about, I will definitely check where if we can borrow some solutions.
Right. Awesome. Thank you so much.
Thank you.
All right, let's see if we have more questions. Marlene?
Yeah, I can circle back with my intended follow-up. Sorry, my battery is running very, very low, so I've been scrambling to figure out how to plug it in. But so to follow up on my last question, I guess sort of what I intended talking about anatomy is certainly it is the case where we need that we need biologically plausible memory. But here I'm also talking about mechanism, and this is getting a little bit into minutiae of semantic pointer architecture and Ningo, but there's also the salient question when implementing any model that does any sort of cognition of what is the mechanism that lies in between memory, in between sort of long-term memory and the representations that appear in working memory, which are not questions that we traditionally answer in cognitive science, and similarly, sometimes not even questions that we answer in the VSA literature. However, if we're building something out in Ningo, the sort of main appeal of it, at least from the perspective of taking a VSA model into neural encoding, besides just like adding a little bit of noise, is that it does compel us to answer this question of mechanism. Is that how do we implement, for instance, this like kind of conditional this mechanism that conditionally queries long-term memory and then retrieves a probe for a retrieve, and then retrieves a probe, and then gets out the answer to our question and then cleans it up. Mm-hmm. What's the mechanism sort of performing this action, and can we make that mechanism in a way that resembles some feature of the brain? Mm-hmm. So clarification done. I guess I'm interested in knowing. I assume you don't have answers to this yet because it's a relatively complex question. But I'm interested in knowing because it seems to me to be the toughest question for me about like how we bridge the gap between VSA kinds of encodings and systems neuroscience. If you have any sort of view on what that mechanism might start to look like that can do this kind of like type-like kind of or this type checking like kind of computation in the brain using a memory system, whatever that may be.
Well, I'm not sure I'm getting your question correct, but isn't this? I think this is what we're trying to do here, or is it one of the sub steps? Like, what is the difference then?
This is certainly part of it, but this is not the whole thing, right? Mm-hmm. So this is a kind of representation level analysis that, with mostly tools provided within the semantic pointer architecture, mm-hmm. one can build out in Ningo almost without regarding the individual neurons, right? You build out you create a bunch of SPA transcodes, you hook up a network, and it performs the computation according to what's set up by your by the connections you put into the code here. Mm-hmm. However, just doing this this is kind of in the sort of cognitive architectures literature, what we call a sort of representation level kind of model. But we also need to talk about, okay, so this we're able to operate on representations, and we're able to build anatomies that operate on representations.
Yeah.
But there also needs to be a mechanism that is able to construct those representations dynamically by controlling different parts of by controlling different like parts of cognition.
Okay. Then maybe if I try again, maybe what I think maybe you're after then is like, where do you get the question and the answer and like those things, that because we have the functions, right? We said that we assume that there are functions like these somewhere in the brain, okay? But how do these questions and answers that you feed into the functions come about, and the propositions, p-types? And then, I mean, I know of two ways. One is through language. And that's, I think, what we touched upon before. Like, you need a way, of course, of taking a string of words in natural language and turn it into one of these structures. And then you can also get them from perception. And then, I mean, like vision. You can see, you can observe a scene, and this, you know, and then you have you should have the visual network will be trained in a way that when you observe a cat chasing a dog, you will have a representation like this occurring in the, you know, the visual cortex somewhere, like through the activity of the neurons. So then you need a vision system. So you need a natural language interpretation system, you need a vision system. That's where the representations come from. But you also need to coordinate everything, of course. Like, okay, you have a question, you have an answer, but how do you know what to use when, and so on? Then you need rules and functions and stuff like that. And those things are in TTR, but we haven't gotten to those yet here. So if I understand your question correctly, then most of what you're asking for is stuff we haven't done yet, but that we are hoping to do from a TTR perspective. And I should have mentioned more, of course, about TTR in this context. There's a huge lot to say about it, but I only wanted to bring in the most relevant stuff here. But it's actually, the reason we want to use it also is that it actually covers a lot of semantic ground. So if you can get a mapping from TTR to SPA, you already have, you're able to handle a lot of different semantic phenomena, like quantification and intentional context and stuff like that. In SPA, so that's why we want to use something like TTR.
I'm certainly interested. I looked at your abstract for the talk, and I tried to find the prior work you cited by your group in it, and I wasn't able to find it online. Can you point me at it?
Yeah, absolutely. So.
We have a mailing list, so if you can, I mean, if you want, I mean, you can post it on the mailing list. So
yeah, absolutely.
Reminder.
Is there any particular paper you couldn't find that I can write it down, or all of them, or?
Well, all of them would be great. I was talking specifically about the one where you were first author.
Okay, the previous. Okay, I see. Sure, absolutely. I will supply that with the. Actually, they might be in these slides, and I can post these slides. I think some of those are here.
Or I mean, I can. I normally, I mean, if you wish, if it's okay with you, I can publish PDF on.
That's fine. Absolutely.
So everybody can see.
So this one, yeah.
Okay, so I see we are approaching the end of our webinar today. So unless we have maybe last question. So Tony, of course, I was waiting for you. So that's why I'm asking for the last question.
Okay.
Go on,
yeah, really interesting stuff, Staffan.
Thank you.
Wondering, so one of the weaknesses in current large language models and generative AI seems to be memory. And I was wondering if you've explored at all how the techniques that you're using here might help improve the performance of AI models on reasoning tasks and tasks that involve accessing, things from memory. So, potentially things like different ways of implementing the circuits, the circuits, what people called circuits in mechanistic interpretation that they discovered in transformers that sort of that they're proposing is how transformer models are doing things like in context learning when they're just retrieving sort of simple facts from context. Just wondering whether you had explored any ideas in those directions.
Okay, thank you. Yeah, that's an extremely interesting question. So, I mean, I think you're talking about like how to put this together a little bit with LLMs, but in or that kind of model, like the transformer kind of model, and like a hybrid architecture. Is
Yeah.
that what you're?
Yeah.
Yeah, I mean that sounds very fascinating. I'm afraid we haven't done anything with that, but that would of course be extremely interesting to do. Um, but then
Yeah.
we would probably. I'm not an expert on LLMs, uh, so I think that would be a really interesting project. But then we need people who, yeah, who have that competence as well. And then the question is if we could contribute anything to that, which I of course hope, but it's I don't have a clear picture of that.
Okay.
But
Okay.
it's a very interesting question. I mean, if you're working on that, I'm interested if you come up with anything.
Yeah. I'm playing around with some ideas.
Okay.
So
Sounds
yeah,
good.
and another question going in a different direction. The sort of reasoning task that you're looking at here is pretty high level. Wondering whether you see any parallels in sort of simpler tasks that don't involve as much sort of conceptual thought, things like object binding in scenes that might be done, that might have preceded the type of sort of high level conceptual
Mm.
reasoning that you've been talking about here, and whether those might use the same mechanisms and neural circuits.
So that's one of the things that I'm not clear about. Like how do you actually get from? So one thing is that you can observe a dog and you can observe a cat and you can observe chasing. Those will all be, and you can all have the activity on the visual cortex corresponding to those semantic pointers. You can have all those active, but how do you make it actually represent this structured have this structured representation instead? And the only answer I have to that so far is that you would have to train on that, to train it to recognize situations, not just individuals and actions. So, and those training vectors would have to be structured basically in the same way. I don't know. We haven't tried it. I don't know if that works, and I don't know what if any supplementary operations and things that could help that. So again, unfortunately, this is one more question that I hope to be able to say. We hope to be able to say something about eventually, but we can't say much about it yet, I'm afraid.
Yeah.
But I hope in this project we at least have a little bit of funding, and I hope we will make some headway towards this.
Okay, thank you.
Thank you.
So I see Gil, you I unmuted. Do you have a question or?
Am I online now?
Yes.
Yep.
I just had one little question.
Mm.
Has anybody heard of HDQF yet?
Not me.
No.
It stands for hyperdimensional quantum factoring. It's taken off like wildfire here.
Mm-hmm.
Maybe it's something that we need to have a talk on.
You mean for fast? associative memories or something.
Yeah, it has to do with the ability to use quantum factoring to part all the ways that a hyper vector is put together. I'm not quite sure how it all works yet, but I'm exploring it.
Mm-hmm.
Go on Copilot and ask about hyperdimensional quantum factoring.
Okay.
Yeah, it's already out there in the circuit, and um, it's a lot of European content in it because of there's a quantum brilliance company in Australia that has a diamond substrate that supports qubit memory at room temperature.
Mm-hmm. Okay. So I think it's useful.
So, yeah, that's reported, was reported, I guess it was in the media recently. And now everybody and his brother are taking a look at it. So, with room temperature quantum memory, suddenly the world has changed.
Hmm.
Yeah.
Okay.
Jill, is that the work by Pratyush Poduval?
I'm not sure. It's in Germany. I'm trying to remember. I've got a brain fart right now. The German company is actually running the process with the Australian company Quantum Brilliance. And I've got some folks looking at it here. It looks like it's not too as difficult as we once thought. And that's one of the reasons that everybody, the people that I'm talking to, are putting everything else aside right now, and they're exploring it. That would be something you need to know because of your company association.
Okay.
That's
All
just
right. So let's see if we do not have any more questions, then I think it's time to wrap up this occasion of VSA Online, and I just want to remind you that in 2 weeks from now we have another exciting talk from Alex Ellery from Carleton University about hybrid artificial intelligence for interstellar missions, which sounds very exciting, and it looks like it's continuing this cognitive hybrid AI topic. So, Staffan, thank you very much indeed for your
Thank you.
excellent talk, and we'll keep in touch.
Yep.
And so, see you all in 2 weeks from now. So, thank you for attending. It was a great attendance today. Thank you, and
Thank you,
goodbye.
everyone. Thank you.
bye-bye.
Thank you. Bye.